Let's take a look at another basis for P2, or another possible basis for P2. I'm going to call this set B, kind of implying that it's going to be a basis. Hopefully I didn't drop a sign somewhere that this actually still is a basis. And here are three polynomials, three vectors from P2, because if you're going to have a basis for P2, all those basis vectors have to be from the space that you're working with. So 1 plus t squared, t minus 3t squared, and 1 plus t minus 3t squared. Let's use coordinates to show that this set B is a basis for P2. Let's stop and think about what we need to see for that to happen. I want to make sure that I can write every polynomial of degree at most 2, that is everything in P2, as a unique linear combination of these B vectors. So to make sure that I get everything in P2, I want a set of vectors that spans P2. When we think of span, we should think pivot in every row. When we want a unique linear combination, that means we want a linearly independent set, and that makes us think pivot in every column. Pivot in every row will make sure that we get everything in P2. Pivot in every column means that we'll get unique linear combinations. So let's name each of these polynomials. B1 of t will be 1 plus t squared. B2 of t will be t minus 3t squared. B3 of t will be 1 plus t minus 3t squared. Now let's write the standard coordinates of each of these vectors. So the standard coordinates of B1 are 1, 0, 1. The standard coordinates of B2 are 0, 1, negative 3. The standard coordinates of B3 are 1, 1, negative 3. So now we have this new fancy polynomial question, and it is the same as old question that we've had before. Is this set of vectors a basis for R3? Is everything in R3 a unique linear combination of these three vectors? And the way we're going to find that out is to put them into a matrix and find the reduced row echelon form. So I'm going to make the matrix B1, the matrix where the columns are the standard coordinates of B1, B2, and B3. We want to make sure that there's a pivot in every row and a pivot in every column. So I'm going to find the reduced echelon form of this matrix. So matrix. Oops. So I've got 1, 0, 1, 0, 1, 1, and 1, negative 3, negative 3. So the reduced echelon form is the identity matrix. Note that I'm not going to say that these matrices are equal because they're certainly not equal. They have different entries. One of the bad habits we tend to pick up in algebra classes is we just put equals between all of our steps. We don't want to make sure that we don't do that here. So you can be mad at me all you want for taking off points and making you redo the problem because you put an equal sign between two matrices that aren't equal, but you're just being mad because I took off points because your answer is wrong. So, I mean, that's like what I'm supposed to do. An arrow is totally okay. Because we were using arrows between, arrow is kind of a standard notation. I tend to not like using an arrow because I always read I always read arrows as implies. And that's kind of a weird usage to me. So I don't personally like it. A tilde is also pretty common between the two. I just leave a space because this is not part of a sentence that I'm writing. This is just me working in the background, writing the reduced echelon form so I could see where the pivots are. And so the matrix has a pivot in every row and column. So since this matrix, B1, B2, B3, has a pivot in every column and a pivot in every row, these vectors form a basis for R3, which means the three vectors B1, B2, the three polynomials, B1, B2, and B3, are a basis for P2. So what this means is that if I grab some vector from P2, it should have a unique set of coordinates relative to these three, relative to this basis. So we should be able to write it as a unique linear combination of these three vectors. So let's grab the vector we had before. I just grabbed my computer and tried to scroll up this way, but this is like in the real world, and the scroll wheel has no control over what's going on with the piece of paper. Yikes. So let's let P of t be, what did we have before? 3 minus t plus 2t squared. And let's find the coordinates of P relative to this basis. Let's find the B coordinates of P of t. That is, write P as a linear combination of the vectors in the basis B. So this is the same as saying write P as a linear combination of B1, B2, and B3. What we're going to do is write coordinates. Actually, let me write down one more way that we're looking at this. So the other way we could think of this is we could say we are solving this polynomial equation. I want 3 minus t plus 2t squared is x1 times this first polynomial plus x2 times the second polynomial plus x3 times the third polynomial. I'm trying to find x1, x2, and x3 that will do this. Now we could multiply by x1, multiply by x2, multiply by x3, just use the distributive property, and then equate the coefficients and make a linear system. But we know what that linear system is going to look like. We're going to do this problem in coordinates. So in coordinates, we want to solve 3, negative 1, 2 is x1 times 1, 0, 1 plus x2 times 1, 0, negative 3 plus x3 times 1, 1, negative 3. Because I want to write P as a linear combination of B1, B2, and B3. Here's what we're trying to do in polynomials. Here's what we're trying to do in coordinates. Here's what the problem looks like in P2. Here's what the problem looks like in R3, because P2 and R3 are isomorphic spaces, because coordinates make everything look like Rn. So now I'm going to look back and say, well, at least I've got most of this matrix plugged into my calculator. I just need to put on one more column to make an augmented matrix. So I'm just going to put everything in coordinates. So 1, 0, 1, 0, 1, negative 3, 1, 1, negative 3. And then I'm just going to make an augmented matrix with the coordinates of P, 3, negative 1, 2. And find the reduced or echelon form. So I'm going to have to edit my matrix. So in the first row, I'm going to have to insert a 3. And in the second row, I'm going to have to insert a negative 1. And in the third row, I'm going to have to insert a 2. So I got 1, 0, 1, 3, 0, 1, 1, negative 1, 1, negative 3, negative 3, 2. And there we go. There are the coordinates, negative 1, negative 5, 4. So the coordinates of P relative to this basis B are negative 1, negative 5, and 4. What this means is if I take negative 1 times 1 plus t squared minus 5 times t minus 3t squared plus 4, 1 plus t minus 3t squared, I should come up with 3 minus t plus 2t squared. So if I take negative 1 times 1 plus t squared minus 5 times t minus 3t squared plus 4, this should equal 3 minus t plus 2t squared. So let's see, I got minus 1 plus 4 is 3. For the t's, I've got minus 5t plus 4t is minus 1t. I got minus t squared plus 15t squared minus 12t squared is 2t squared. So everything checks out. That's a great thing about math. If you're doing math problems and your task is to solve an equation, you can always just make sure that you're right by seeing if your answer satisfies the equation that you were trying to solve. So here we have the coordinates of P relative to B were negative 1, negative 5, 4. So that's how we write P as a unique linear combination of the vectors in basis B. But we can go the other way with this as well. If I give you a set of coordinates, I can ask you to find out what the vector is. So let's do that problem. So same basis B, which is 1 plus t squared t minus 3t squared, 1 plus t minus 3t squared. And I called this b1 of t, b2 of t, and b3 of t. So in the previous problem, I gave you a vector and asked for the coordinates. So let's suppose that I told you the coordinates. Suppose that the coordinates of some polynomial x of t were 2, -3, and 1. I could ask you to find x of t. Uh-oh. So let's suppose that we're given an x of the coordinates of x of t, oops, relative to b. Yikes. Suppose the coordinates of x relative to b are 2, -3, 1, and I want to find the vector x of t. One thing that we can do is just take these coordinates and read what the coordinates are telling us, what the coordinates mean. It's 2 times the first vector minus 3 times the second vector plus 1 times the third vector. So x of t is just 2 times b1 of t minus 3 times b2 of t plus 1 times b3 of t. So we could do this whole problem in polynomials. It's just 2 of these, 1 plus t squareds, minus 3 of the t minus 3t squareds, plus 1 of these 1 plus t minus 3t squareds. And so we'll have 2 plus 1 is 3. The t parts will have minus 3t plus t is minus 2t. And 2t squared plus 9t squared is 11t squared. Minus 3t squared is 8t squared. I'm doing arithmetic, so you got to watch me because I might be messing something up. So in this case, I gave you coordinates, and we found the polynomial that has those coordinates. So this is just the classic algebra input-output game. I can give you an input and ask you to find an output like we did here. You just kind of plug things in. Or I can give you an output and ask you to find an input, that is, solve an equation. If there's an x and a y, I can give you an x, ask you to find y, or I can give you y and ask you to find x. The classic algebra input-output game. In this case, I can give you coordinates and ask you to find the vector, or I can give you the vector and ask you to find the coordinates. In one case, you're just evaluating, and in the other case, you're solving an equation. What we want to look at here is a more matrixy version of this problem. I have the coordinates of x relative to b, and I want to do this problem in coordinates because it'll point out something that's kind of important to notice. So there should be, oh, sorry, go ahead.
How did you get -2t?
I just looked at all the t's. I don't have 0t from here. I have minus 3t plus 1t.
Oh, okay.
That's my minus 2t. I just multiplied this out. I didn't want to write all the distributive property. So what we want now is kind of a more matrixy version of what's going on. How do the coordinates and how do the standard coordinates and the B coordinates, how are they related? So that is an important question. What's the relationship between the B coordinates and the standard coordinates? So we need to look at the relationship between B coordinates and standard coordinates. So I'm just going to write it down. If I make the matrix that we used before was the coordinates of B1, the standard coordinates of B1, then I took the standard coordinates of B2 and the standard coordinates of B3. So notice that these are the standard coordinates. The columns here are the standard coordinates of the B vectors. That matrix is the standard coordinates of the B vectors. If I want to put this matrix, the equation that we solved before was this matrix multiplied by the coordinates of P relative to B, and that gave us that'll give us the standard coordinates of P. That's the equation that we solved before. So if I multiply this matrix where we have the standard coordinates of the B vectors by the B coordinates of some vector, so if I take the standard coordinates of the B vectors and multiply by the B coordinates of x of t, this should give us the standard coordinates of x of t. Now I multiply a matrix by a vector, I'm going to end up with a vector, not a polynomial. So I have to make sure that over here on this side, we are looking at the standard coordinates and so here's the matrix equation that gives us the plug something in, plug in the inputs to get the outputs, or plug in the outputs and solve for the inputs. Let's verify that this works. If I take the vector, the standard coordinates of the B vectors, that's 1, 0, 1, 0, 1, negative 3, and 1, 1, negative 3. If I multiply this by the B coordinates of x of t, which were 2, negative 3, 1, so I get 2, 0, 1, 2 plus 0 plus 1, which is 3. Then I get 0 minus 3 plus 1 is minus 2. And I get 2 plus 9 minus 3 is 8. So here are the standard coordinates of the B vectors multiplied by the B coordinates of x. Then we'll get the standard coordinates of x. Notice that I'm not just saying the coordinates because there's lots of different coordinates. The standard coordinates of the b vectors, the b coordinates of x, and the standard coordinates of x. Sorry, I keep hitting the table and making it wobbly. Blair Witch Project style. So for those of you who've gone further in chapter 4, all that we need to do now is look at two different bases for a vector space, say a b basis and the c basis, and replace standard coordinates with c coordinates. So if we have the c coordinates of the b vectors multiplied by the b coordinates of a vector, that will give you the c coordinates of a vector. So we just replace standard coordinates with c coordinates, and that will allow us to change from one basis to another basis. What you really need to see here is how we take these polynomials and think of them as vectors. Then once we think of P2 as R3, all of chapter 4 becomes chapter 1 and chapter 2. This is the other reason that determinants are annoying, because they put determinants in this book as chapter 3. So, but conceptually, chapter 1 plus chapter 2 is equal to chapter 4. So if chapter 4 was chapter 3 and chapter 3 was moved to its proper place as an appendix, because that's where determinant should be, then chapter 1 plus chapter 2 would equal chapter 3, not only numerically, but like conceptually as well. Oh well, missed opportunity, Dr. David C. Lay. All right, let's pause the video here, take a minute and come back and talk a little bit more about coordinates and why everything is Rn.